Forgive me, audience, for I have sinned. It has been nearly 2 years since I last returned to the topic of my most popular video, and in that time, YouTube has seen fit to dethrone it as the top suggestion for the search term Proxima B. I'm not bitter. I have been a negligent gardener, and beds must be tended, or your blooms will choke. But in retrospect, it does make my hesitant self-award of the title YouTube's unofficial ambassador to Proxima B somewhat presumptuous. Please do not confuse my negligence with inattention. I have maintained a distant paternal interest in the welfare of my peculiar charge. It's simply that, for all the discoveries made in the Proxima system since my last visit, none have truly stoked my fires. My overwhelming fascination with Proxima B is as a possible abode for life, and science has collectively been doing its utmost to douse that hope in piles of dead sand in the months and years since I last admitted it. Fool that I am, I refuse to accept such a bleak vision of the universe, and I have scientists who, even now, agree with me. You can call me a wishful thinker, but I'm a wishful thinker with reliable sources. Let's get the simple stuff out of the way first. Yes, Proxima B exists. This may seem self-evident, but believe it or not, until May of 2020, we didn't actually have an independent confirmation. That confirmation came courtesy of a team led by Alejandro Suarez Mascareño of the Astronomical Institute of the Canaries and Mario Damaso of the Astrophysical Observatory in Turin. The team employed the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations at the European Southern Observatory's Very Large Telescope in Chile. If you didn't notice, that name produces the very European acronym of ESPRESSO. ESPRESSO was essentially a souped-up version of the High-Accuracy Radial Velocity Planet Searcher, or HARPS, that found Proxima B back in 2016, just 10 times more powerful. It was able not only to confirm the planet's existence, but also to narrow its mass estimate to 1.173 plus or minus 0.086 Earth masses, meaning Proxima B is far closer in form to an Earth than to a super-Earth. More astounding still, they found a possible additional 5-day wobble in Proxima B's signal, which may be caused by a moon 3 times the mass of Mars. Also, in May 2019, a separate study using 48 hours on the Spitzer Space Telescope has shown, conclusively, that no, Proxima B is not transiting its star. Though, since it only had about a 1% chance of doing that anyway, that wasn't too surprising. The most dramatic development in Proxima B's neighborhood in my absence had little to do with it at all. In January 2020, another Damaso-led team announced the tentative discovery of a second planet in Proxima Centauri's court, christened, naturally, Proxima C. Like its sibling, Proxima C is a super-Earth, though unlike it, at 7 Earth masses, it is closer in form to Uranus and Neptune than to our own world. It was found using HARPS, the same instrument that found Proxima B, and via the same method, radial velocity. Radial velocity means observing a star's spectrum for the tiny red and blue shifts as it wobbles in response to the gravitational pull of an orbiting companion. It showed that Proxima C's orbit is about 1.5 AU, roughly that of Mars, though because Proxima is so much smaller than our Sun, the planet's orbital speed is far slower, and its year lasts 1900 days, nearly 3 times longer than Mars's. Of course, Proxima's dimness also means that C is witheringly cold, a mere 39 degrees above absolute zero, comparable to Neptune's moon Triton, the coldest object in the solar system. As well as discovering Proxima C, the team were able to determine a number of things the Proxima system is not. For instance, it is not home to a Neptune-sized planet out to 1 AU from its star, or a Saturn-sized planet out to 10 AU. They also found that Proxima's Hill sphere, the maximum range at which an object could maintain a stable orbit, was just 1700 AU, or about a tenth that of the Sun, due to the gravitational influence of the Alpha Centauri binary. the team expected they would have to wait at least one of Proxima C's years, or about 5 Earth years, before their planet could be confirmed. They reckoned without good, old-fashioned, brute force astronomy. In June 2020, just 5 months after the initial announcement of Proxima C, Fritz Benedict, an emeritus senior research scientist with McDonald Observatory at the University of Texas at Austin, announced that he had independently confirmed Proxima C using that most primeval of all planetary detection methods, astrometry. For those who've not watched my video on Barnard's star, astrometry is the precise measurement of the distances and motions of stars. Rather than relying on spectrographs, as with the better-known radial velocity method, astrometry involves simply staring at a star and trying to tease out the wobble in its motion directly. As a planet detection method, astrometry is notoriously buggy and led to many false positives in the early years. With the rise of radial velocity, it was largely abandoned, though since then it has been used to find at least one planet. Benedict believed he could find another. Indeed, he believed he had already found it. Over 2 decades prior, Benedict and his colleague Barbara MacArthur had repurposed the Hubble Space Telescope's fine guidance sensors, instruments primarily used to accurately point the telescope, to conduct astrometric searches for planets around Proxima Centauri. Understandably, they have restricted their search of the Hubble data for signals shorter than 1,000 days, and found none. Benedict decided to revisit the data to search for longer signals. And lo and behold, buried in the reams of 25-year-old Hubble data was a wobble lasting 1,907 days, the precise orbital period of Proxima C. This was about as rock-solid a confirmation as was possible to get. But even so, Proxima C's existence caused consternation. Models of solar system formation had suggested that the snow line, the boundary beyond which ice becomes dominant over rock, acted as a barrier at which icy material could accumulate. As it approached the Sun, ice evaporated, and then refroze, creating a massive pileup. It is not considered a coincidence that Jupiter lies just beyond the snow line. With that much matter to feast on, it could grow gigantic. But Proxima C lies at 1.5 AU, 10 times farther than Proxima's snow line. How it could have become so large, so far from its tiny star, is a mystery, though it is possible that it migrated to its current position. The confirmation of Proxima C opened an intriguing possibility. The large relative distance between the planet and its star meant that it could be imaged directly. In June 2020, after a heads-up from Damaso, a team led by Raphael Gratton of the Astronomical University of Padova in Italy turned the Spectropolarimetric High-Contrast Exoplanet Research Instrument, or SPHERE, an adaptive optics system on the Very Large Telescope specifically designed to image exoplanets, toward Proxima Centauri. Unfortunately, imaging Proxima C would, as Damaso noted, push SPHERE to its limits, and the resulting data were open to interpretation. Of the 19 suggestive images, one immediately stood out as 6 times brighter than the surrounding noise. Bingo, you might think. Except it was too bright. A planet of Proxima C's mass 4.2 light-years away would appear between 10 and 100 times dimmer than this prospective planet. If its brightness were due to size, then it would be 5 times the mass of Jupiter, or 200 times more massive than it appeared to be. Also, its calculated motion did not jibe with the observed motion for Proxima Centauri. One explanation for the planet's apparent brightness was that it was surrounded by a large mass of reflective material, perhaps a dust cloud or even a gigantic ring system up to 4 times as wide as Saturn's. While possible, this seemed ridiculously unlikely. Proxima is a relatively old star, about 1 billion years older than the Sun, so its planets should be similarly old. Cassini's study of Saturn's rings had suggested that they were relatively young, at 100 million years, and unlikely to last another 100 million. No one could see how a planet could retain such a vast ring system for so long a time. Of course, the image, while unlikely to be an artifact, maybe of something else entirely. We're still feeling our way. And now, we must return our gaze to Proxima B, and examine why many appear to have given up on it. The pessimist arguments all boil down, if you'll pardon the metaphor, to one fact. Proxima is a flare star. And I don't plan to argue that. Over the course of 50 days of observation, astronomers saw Proxima emit 72 flares. The star spent nearly 7% of its time flaring. In fact, Proxima forced me to grapple with a new word: superflare. A superflare is usually defined as releasing 10 to the 26 joules of energy, or about 10 times the amount released by the largest solar flare in recorded human history, the Carrington event. And we have seen Proxima unleash 2 of them in the last 3 years. In 2016, Proxima released a superflare 30 times stronger than normal. The flare increased Proxima's brightness by a factor of 68, enough, astoundingly, to briefly render that sputtering campfire spark visible to the naked eye. Those are just the ones we've seen. Estimates suggest they may be 5 times more frequent. In contrast, our Sun is expected to launch such an attack just once in a millennium. And of course, Proxima's planets orbit far closer to its raging surface than the planets in our system. Flares flood a planet with ultraviolet light, which can ionize and break apart vital atmospheric gases like water and ozone, which in our atmosphere acts as our main defense against ultraviolet radiation, and even deplete or erode an atmosphere over time, as has happened to Mars. If these flares were infrequent, then a planet's atmosphere might recover with time, but the constant barrage faced by the planets of Proxima Centauri does not offer time for such recovery. In addition, the planets' closeness to their stars may cause their magnetic fields, if they have them, to buckle and shrink, enfeebling their defense against the stellar wind. In October 2019, Alison Farish, a graduate student at Rice University, modeled the interaction of red dwarf exoplanets like Proxima b with their stars' extended magnetic fields, and concluded that they would completely lose their atmospheres in as little as 100 million years. A mere season in an age of the star system. Models have long suggested that during its even more violent early phase, Proxima could have blasted an ocean's worth of water from B's surface. In fact, observational evidence, the best kind, suggests it may be worse even than that. In January 2019, a team led by John Wisniewski at the University of Oklahoma in Norman observed a debris disk around a young red dwarf star named AU Microscopii. They observed what appeared to be blobs large enough to stretch from Earth to Jupiter, traveling at the star's escape velocity, driving out the icy material at the disk's edge. The blobs may be caused by massive flares stirring up the stew of planetary formation, possibly driving all water out of the system before it has a chance to fall back onto any nascent terrestrial planets. If AU Microscopii's behavior proves the norm, then planets around red dwarfs could be dry, barren rocks. If that wasn't enough, in June 2019, a team at UC Riverside calculated that planets orbiting red dwarf stars like Proxima would require tens of thousands of times more CO2 in their atmospheres to maintain a temperature sufficient for liquid water. While this may be enough for your basic bacterium, anything more advanced, at least that we know of, would be poisoned. On top of that, radiation from the star can break carbon dioxide into carbon monoxide, which is even more lethal. Then there is the ultimate face slap, the crowning kick in Proxima B's keister. It's not enough that they have stripped it of its vitality and left it a desiccated, blasted heath. They've also managed to drag Proxima C into this lynch mob. In June 2020, Abraham Loeb and Amir Siraj of Harvard argued that Proxima C could be Proxima B's nemesis, in more ways than one. In our solar system, Jupiter is the primary shaper of the asteroid belt. Its gravitational influence clears out regions known as Kirkwood gaps, thanks to what are called resonances. A resonance is a gravitational relationship in which two objects' orbits exist in a precise ratio, say 2 to 1 or 3 to 2. When this happens, the gravitational tugs can eventually throw an object out of an orbit, sending it into the inner solar system. This is the main cause of most asteroid impacts on Earth. But believe it or not, Saturn also sculpts the belt, albeit at a far slower and deeper level. Saturn's precession is in resonance with the orbit that marks out the belt's inner edge. A precession, essentially, is an orbit of an orbit. As Saturn orbits the Sun, over an immense span of time, its orbit also rotates, completing one cycle every 2 million years or so. This resonance clears the inner edge of the asteroid belt, honing it to its current sharpness. It also plays a direct role in the rate of impacts on Earth over time. An asteroid 300 kilometers across, with a mass of a few quadrillion tons, would be enough to vaporize all water on our planet, should it collide with it. And Saturn has about a 1% chance of sending one of those our way in the next 5 billion years. Loeb and Siraj estimate that if an asteroid belt exists between Proxima C and B, with a mass of about 1/10,000th that of Earth, about a third the mass of our asteroid belt, and located at either 0.3 or 0.5 AU, the numbers are surprisingly specific, thanks to a precession resonance with Proxima C, a strong possibility exists that Proxima B has been sterilized by such a massive impact at some point in its past. Of course, this all hinges on the existence of a belt in the relatively small region between Proximas B and C. And unfortunately, that's looking fairly likely. In 2017, a team led by Guillaume Anglada, the discoverer of Barnard Star B, using the Atacama Large Millimeter Array, or ALMA, detected a dust belt around Proxima Centauri with a mass believed to be roughly equal to our own Kuiper belt. They estimated the belt to extend between 1.3 and 4 AU from the star, which of course places it far outside the grasp of Proxima C. But the team also found faint signals of other belts farther in. Since Proxima C lies at 1.5 AU, square in the middle of the belt, astronomers are slavering to get another look at ALMA to see how the planet and the belt interact. Again, none of this evidence places the gun in Proxima C's hand, but should we find that Proxima B was indeed murdered, C would certainly have means and opportunity. So, it seems Proxima B just can't catch a break. But there are dissenters to this view, and because I refuse to let the scientific establishment dogpile Proxima B, I will now focus on them. To be fair, it is much easier to be optimistic about the possibility of life if you don't restrict yourself to the kind of life watching this video. If, say, you'd be happy with a biosphere of organisms no more advanced than yeast, then the options for habitability suddenly explode. And let's be honest here, a fully alien biosphere, a complete independent replay of evolution, would be a massive leap in scientific understanding, however yeasty. In February 2020, a paper by Jimena Abrevaya et al. In the monthly notices of the Royal Astronomical Society suggested that the unending pessimism of the Proxima deniers may be due to false assumptions. The amount of ultraviolet on the surface depends deeply on what kind of atmosphere it passes through. Many studies of UV effects on the surface of Proxima B have assumed an O2-rich, Earth-like composition for the planet's atmosphere, but such an atmosphere would almost certainly be stripped off by flare activity so close to its star. Conversely, an atmosphere richer in carbon dioxide can actually prevent nitrogen and oxygen loss because, while it traps heat from the surface in its lower atmosphere, it actually cools the upper atmosphere, since, in that far more rarefied region, any heat it emits from being jostled by another molecule is far more likely to dissipate into space than be reabsorbed. This atmospheric composition is believed to have protected early Earth from the young sun's violent outbursts. The team modeled a number of what they considered to be more realistic atmospheres for a hypothetical Proxima B. One consisting purely of carbon dioxide, one of 10% carbon dioxide and 90% nitrogen, one of half carbon dioxide and half nitrogen, and one of 90% carbon dioxide and 10% nitrogen, similar to Venus or Mars. Pressures at the surface were set variously at 10, 20, 50, 100, 200, and 500% that of Earth. Assuming an average energy for a typical flare of 2.5 times 10 to the 23 joules, that would produce an average surface flux of roughly 7 watts per square meter. Superflares would result in a release of 10 to the 34 joules, leading to a flux of 92 watts per meter. The team found that, for the dominant ultraviolet range of 315 to 400 nanometers, so-called UVA, even without an atmosphere, the surface flux was just 1.98 watts per square meter, less than 2% what Earth receives. With the modeled atmospheres in place, the numbers fell even farther. More dangerous UVB and UVC wavelengths could be absorbed by CO2 in the atmosphere, assuming a pressure twice that of Earth's. The team then repeatedly subjected 2 very different microorganisms, Haloferrax vulcanii, an archaeon only found in hypersaline environments, and Pseudomonas aeruginosa, a garden variety bacterium, to those surface UV levels for times ranging between 5 and 4,500 seconds to simulate regular flares, or 420 seconds to simulate superflares, in accordance with previous models. They found that while the survival rates at the start were as expected for microbes exposed to UV radiation, the survival rates increased dramatically after the population had fallen to less than a millionth its former level, indicating that a certain number of microbes possess an innate resistance to UV effects. In December 2019, Lisa Kaltenegger and Zifan Lin of Cornell University's Carl Sagan Institute, a place I would work at merely on principle, suggested a number of biological defenses that organisms could use to survive in a high-radiation environment around an M-dwarf star. The most obvious is the method that optimists believe protects life on Mars, living underground, or, in presumably cozier environs of Proxima B, underwater. A relatively thin layer of soil or water would effectively shield any nascent life from UV radiation. Many microorganisms also possess pigments and methods to repair their DNA that aid in reducing UV damage, or even preventing it altogether. One ingenious possible method is biofluorescence. Unlike bioluminescence, which is light produced through chemical reactions, biofluorescence occurs when an organism absorbs light at a high wavelength, usually blue, and then re-emits it at a lower wavelength, usually green, orange, or red. By effectively slowing the rate of photons, biofluorescence can neutralize UV radiation and convert it into a less harmful form of light. They also note, as have many astrobiological optimists, that, for all its dangers, UV may actually be crucial to the formation of life, as certain prebiotic chemicals require UV to form. And given that red dwarfs like Proxima emit far less UV than larger stars like our Sun, flares may be the only energy source great enough. In January 2019, Kaltenegger and her Sagan Institute colleague Jack O'Malley James compared models of the current state of Proxima B to those for the early Earth. They noted that, while flares could have removed an ocean's worth of water in Proxima B's early years, there's no reason to assume that Proxima B did not begin life with far more water than Earth, assuming, of course, that Proxima was a more graceful child than AU Microscorpii. While yes, it is entirely possible, as many have suggested, Proxima B has been left an airless wasteland, could just as well have an atmosphere and much of its liquid water, either across the entire sun-facing side or in a tropical belt. All the horror stories about Proxima B's activity play down one fact. Red dwarfs are small, and Kaltenegger's models for both Proxima B and TRAPPIST-1e suggest that the UV flux at their surfaces, even during flare events, barely exceeds that produced by our own Sun. And even if said flux exceeds that of the Earth now, it is nowhere near as strong as on early Earth, 3.9 billion years ago, when life was already forming. And beyond that, atmospheric composition can aid in blocking ultraviolet radiation, with both ozone and CO2 acting as sunscreen. And even models with severely eroded and anoxic, and thus ozoneless, atmospheres, Proxima B still receives 10 times less UV than early Earth. Professors Manas V. Lingam and Abraham Loeb, again, of Harvard, have actually used that as an argument against life on Proxima B, saying that Proxima could not emit enough high-frequency light to enable photosynthesis. I admit, I'm too close to this. I've grown rather fond of Proxima B and the various worlds envisioned for it. It would truly break my heart if it was revealed to be a simple, airless rock. But the issue will soon be resolved one way or another. Lynn and Kaltenegger suggest that the next generation of telescopes, such as the James Webb Space Telescope, the Giant Magellan Telescope, the 30-meter telescope, and the Extremely Large Telescope, will be able to directly image Proxima B, and perhaps even detect the gases in its atmosphere. Whatever world Proxima B turns out to be, I will soon have to live with it.